Okay, all right. All right, good afternoon, everyone. This is Dr. Carl Ng. Welcome to the Quantum Science and Computing webinar. This is a event which is hosted by the Asia University Department of Bioinformatics and Medical Engineering, Asia University at Taiwan. I'm one of the co-chair of this activity in the collaborate with Professor Chien-Hung and Mr. Alex Sun. We have added a website for this quantum webinar event. The URL address is https://quantum.asia.edu.tw. You can follow this link, and this will carry you forward to this web browser. And then click on this link. This will forward you to another homepage. That is the Quantum Science and Computing free online forum. Now, please use this link to sign up. So if you follow this link, then this is the Google form for that we prepare for this activity. So please scroll down your web browser and then fill in your personal information. Just sign up once, no need to do it again. Okay, we will keep the record in our backend. Now on this website, we also have a link for the call for presentation. We'll welcome you to visit this page and then download a form and then fill out the detail of your talk title and your personal information, and then email it to qphysics@gmail.com for approval. Now we will do the video recording, and subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 5 days after the presentation. Now today is April 23. Now it's 14 p.m. at Taiwan and 13 p.m. at Jakarta. And the title of today's talk is Quantum Simulation Algorithms for Quantum Computers. The speaker is Mr. Paul Chien-Hung. He's from National Taiwan University at Taiwan. So let me give a brief introduction for our speaker today. Mr. Paul Cho is a PhD student in the Department of Physics at the National Taiwan University, specializing in quantum algorithm development for Hamiltonian simulation and optimization. He actively engaged in exploring the frontier of quantum computing through his research. With a passion for practical application, he has contributed to several successive projects, including coaching winning teams at IBM Qiskit Hackathon, held by NTU IBM Q Center in both 2020 and 2022. And additionally, his work has been recognized and selected for presentation at the conference Theory of Quantum Computation, Communication and Cryptography, TQC, in 2023. So today, Paul is going to deliver a presentation on quantum simulation algorithms for quantum computers. And I just asked him, he said you can interrupt him at any time for any question. He welcome your interrupt and ask questions. So don't hesitate. Just switch on your microphone in case you have anything you want to have more details from Paul. So without further delay, so let me pass my microphone to Paul.
Okay, thank you for your kind introduction. And
So,
my name is
yes,
Chien-Hung. So now I'm going to share my screen.
yes,
Hold on a second. Um,
yes, yes, I can see your desktop.
okay. Thank you for inviting me here to present my work. Um, my name is Chien-Hung, and today I'm going to present my joint work with Dr. Barry in Macquarie University and Dr. Xie in Foxconn Quantum Research Institution. So this work is already posted on arXiv, and it was just accepted by the journal Physical Review A recently. And today I'm going to share this work with you. And the title is the double linear error order of approximation via randomized product formula. So today my talk, I will split it into three parts. First, I'll introduce the motivation, like why we want to study this kind of topic. And the second would be like I'll introduce you several state-of-the-art quantum algorithm that they use those algorithms to simulate the physical system or some chemical system. And the last part, I will introduce you my work that is using some randomized technique to increase the accuracy of the product formula. The product formula is one kind of the algorithm that they use to simulate the physical system. So before we dive into our work, so I want to introduce that there are several applications of quantum computers. Like first, we can use quantum computer to break RSA algorithm, and that is the famous Shor's algorithm. And the second one is that we can use a quantum computer to solve some optimization problem. There are several kind of optimization algorithms have been developed, such as quantum annealing and QAOA algorithm, which is the hybrid quantum classical algorithm. And the third one is also an important application of quantum computer. That is, we can use quantum computer to simulate the quantum system and study their dynamics and properties. So let me quote a sentence from Richard Feynman. He said that nature is not classical. And if you want to make a simulation of nature, you have better make it quantum mechanical. So this means that because actually our world has also some quantum nature. So quantum computer actually is the best platform for us to simulate our physical process in our real world. But the truth is that currently our quantum devices is not that perfect. Sometimes uh, current quantum devices will suffer from some errors, such as limited coherent time, and also the amount of qubit is not enough for us to conduct some large scale application. So if we want to use a quantum computer to study the quantum system, then we need to efficiently and accurately construct the evolution operator with elementary grade. This is a it is a pivotal issue. So like there are several aspects that we need to care about, like the number of elementary gate that we use, and also the number of qubit that we use in our quantum devices. So like because now we are in a NISQ era, so we cannot use too many elementary gates, and also the the requirement of the number of qubits should not too large, and we need to try to find a clever algorithm that can efficiently and accurately construct the evolution operator. So actually, we can formally restate the problem of quantum simulation in this way. Here, we consider the time-independent Hamiltonian, and given a system Hamiltonian edge, and the dynamics of the system is given us the, if we want to get the state as time equals to small t, then we can implement an evolution operator onto the quantum state psi 0. Then our goal is to try to construct a quantum circuit U to approximate the exact unitary operator exponential minus I ht. So here we want to find a clever so that it efficiently approximate the true exact unitary operator exponential minus I ht. So let me give you an overview of how to obtain the effective Hamiltonian in the field of quantum chemistry. So like in quantum chemistry, like we all know that it's a very complex electron system. So the Hamiltonian of this electron system should contain the interaction between electron and the interaction between nuclear and also the interaction between electron and nucleus. And in quantum chemistry, like we can, if the mass of the nuclear is way larger than the mass of electron, then we can use the Bohr-Oppenheimer approximation to reduce it into this form. And it contains the kinetic turn of the electron and the interaction between electron and nuclear, and the interaction between electrons. So then there are several ways that you can choose to transform this Oppenheimer approximation onto the qubit form. The qubit form means that the form that we can implement it on universal quantum computer. So then here at step 2, we could transform it into the second quantized form. So it means that we need to choose a set of bases, and we use the raising and lower operator to represent this effective Hamiltonian. And the basis of the information of this basis is included in the coefficient HPQ and HPQRS. So then after we have the second quantization form, and we can encode it onto qubit form. So here I provide a very common transformation, that is Jordan-Wigner transformation. So it is simply just store the occupation number of spin orbital into the 0 and 1 state of the qubit. So here the F means that F0 means that the zeros spin orbital, and then we can map it to the m qubit, and when F0 equal to 0 means that the zeros spin orbital is with the zero electron, then we can use the zero qubit let the zero qubit to be in the state 0 to represent that spin orbital has no electron on it. Then we can use some Pauli string to actually transform those raising and lowering operator to represent it into a Pauli gate form. So then after this procedure, then we can actually transform the Hamiltonian of the electron system into the qubit form. So then here I provide you 3 cases, like one is SN, and second one is carbon dioxide, the third one is propane. And as it turned out that when we consider this kind of molecule, the size, the number of terms in Hamiltonian is, like for example, in SN is around 241,000 terms in it, and it requires 46 qubits. And if we want to calculate carbon dioxide, it also requires 113,000 Hamiltonian terms, and it requires 54 qubits. So this shows that actually when we want to do the application and to simulate the real molecular structure, then the size of the Hamiltonian will be very, very complex. And this moment, it come up with the question, how to effectively and accurately simulate Hamiltonian with lesser resources? So that's actually this is the motivation why we want to find a efficient and accurate algorithm to simulate the quantum simulation. So if there is some question, so please feel free to ask me. Then next, I'll move on to formally restate the problem of Hamiltonian simulation. So given the Hamiltonian is a sum of the several local terms here. The local term means that the term is locally acting on the certain qubit, and V is the evolution operator, like I just mentioned before. And the goal of Hamiltonian simulation is to construct an operator U such that the distance between U and the evolution operator V is lesser than epsilon. And here we need to, if our evolution time is t, then we need to divide evolution time t into sufficient large R steps. So if epsilon is at the order of big O t over R to the power of k, then we say that this Hamiltonian simulation scheme is of error order k. So then here I list several well-known Hamiltonian simulation algorithms. The first three method is the product-based formula, which I will introduce later. And then the next is the truncated Taylor series, which is they use the Taylor series expansion to realize the evolution operator, and the last one is quantum signal processing. And quantum signal processing is the kind of its procedure is kind of like a Groover algorithm, and they utilize the structure of the Groover-like procedure, and then they use some signal processing to help them to simulate the dynamics of the quantum system. So here, truncated.
One question.
Yep.
What is the capital letter L? L is the number of terms in the Hamiltonian.
Yeah, that's
Big
true.
L.
Here, big L is the
Okay.
number of turns in Hamiltonian here, and
Okay.
here,
And how one determine up to how many terms we should keep?
you mean in truncated Taylor series case, or
Yeah, in the truncation, how many terms we have to keep? Is there a is predetermined or it is a
that's a good question.
undetermined number?
Yeah, the term that we want to truncate it is predetermined. Like depend on what the accuracy that you want to simulate the process, then we can determine the order that we want to truncate it. So then when we truncate the order, then we can use some technique, like we can sum over those unitary and to realize the evolution operator. So actually it's predetermined.
So it is fixed by epsilon. Once you fix epsilon, then you determine L, or the other way around. You assign a number for big L, and then you decide epsilon.
Actually, we would decide like the t is the total evolution time. Then we decide the evolution time that we want to simulate, and epsilon is also depend on your requirement. Like if we are consider chemistry application, the epsilon would usually it would be 10 to the power of -6, and then we can follow the procedure that I mentioned in the previous slide. We could obtain the effective Hamiltonian, and then we can obtain its structure. So actually, I forget to put the form of the alpha here. Alpha here, which is related to the structure of the Hamiltonian edge. So I do not show here explicitly, but you can realize it is a vector which could describe the structure of the Hamiltonian here. And actually, there's some hidden vector and here, and I didn't show it. But here, I just want to reflect the fact is that the gate complexity depend the gate complexity when we consider gate complexity with respect to time t and Hamiltonian L and epsilon, then we can compare them in this way. And so I'm not sure if I answer your question.
So L is predetermined.
Yeah, L is predetermined. Like we can obtain the effective Hamiltonian according to my previous slide, and we can use the Born-Oppenheimer approximation and second quantization, and then the Jordan-Wigner transformation. Then we can obtain the form of the Hamiltonian edge, and the edge usually we can write it as the dimension of some local term here. So then L is determined.
So is it a guidance or say for carbon dioxide or for the organic molecule? Is it that there's some guidance how many terms we should keep? See, here is on the order of a few 100,000, right?
Yeah.
So
So
usually LO is of this kind of order, about 100,000 terms, something like that.
yeah. So actually, there's several approximation in it when we want to get their effective Hamiltonian. So, and also it also depends on the basis that we choose. So there's quite a lot of factor here. It will affect the form and the value of L here and the number of qubit usage here. So yeah. So
Yeah.
L is pretty determined. Once your molecule is fixed, and you can determine to what sense the L is some value, and then you can write it into some local term here, summation of local term. Then you can decide like what algorithm that we can use. Like you want to use some product based or use some not product based quantum simulation algorithm.
Okay, all right. So usually you use an STO basis, is that right?
Sorry, could you say?
You use the STO basis.
Oh yeah. In chemi they sometimes they use the STO3G basis, but like in there's many study they say that they can use different kind of basis and they can achieve different effect there. So actually, this is a quite active research area. So
I see. Okay.
yeah.
Okay. Yes. Thank you.
Okay. So then, although like I just mentioned before, truncated Taylor series, when we consider the complexity with respected to epsilon, is a logarithmic 1/epsilon, and the quantum signal processing is the linear. Its gate complexity is linear in time. So actually, it shows that when the evolution time is large, some quantum signal processing would have some advantage compared to the product-based formula, because product-based formula, like in first order product formula, is a t square, and in 2k order product formula is a t to the power of 1 plus 1/2k. So like there's actually when we consider the factor of epsilon and time t, truncated Taylor series and sub-quantum signal processing will have some advantage here. But there's a but. Product formula are still very competitive. Here's some reason. First, actually, product formula, when we use product formula, we don't require any ancillary qubit. And this is very important reason for our current devices, because in our next era, we cannot have too many qubits that we can use. So we need to use the qubit wisely. And the second term is that sometimes when we consider some internal structure of Hamiltonian, product formula will perform better than the other two. And third is that although other algorithms have logarithmic dependence on the error epsilon, but in our practical application, we will fix this error to some value. Like in chemical application, we'll fix epsilon to be 10 to the power of -6. Then the algorithm only provide polynomial reduction with time t in gate complexity. So it shows that it is still worthy to study product formula and to find some way to improve its accuracy. And here's the plot from the Andrew Trust paper in 2018. And here they want to evaluate the qubit usage when they simulate the unsigned Heisenberg model. Heisenberg model is the effective Hamiltonian model that they use this to describe and to study the critical property and the dynamic property of magnetic system. Here they impose the periodic boundary condition, and they compare three kind of quantum simulation algorithm. First is product formula, which is in red dot, and the second one is TS, means that it's Taylor series, and the blue dot is the QSP, the quantum signal processing. So it shows that actually when we simulate the system size from like 5 to 100, the qubit usage of the lesser than the other two, truncated Taylor series and quantum signal processing. So it means that product formula is still very powerful. Yeah. So here we move on to our third part. I want to show our result here. Yeah, I'll try not to show too many mathematical details here. So I just want to share some important fact about our result here. So when we consider the two case or the randomized product formula, our method, randomized method, can double the error order from 2k plus 1's order to 4k plus 2 order. So which means that we can use the almost the same amount of quantum circuit, and we can make the simulation to be more accurate than the previous method. So when L is at the order of little o, d over epsilon to the power of 1 plus 1 over 2k, our method is advantage over the existing higher order product-based algorithm. So here's the table. The table shows that the first one is the method proposed by Andrew Charles, and which is they also try to implement some randomized technique in product-based formula, and they have this kind of gate complexity. It's maximum over these two terms. One is the t is added to the power of 1 plus 1 over 4k plus 1, and the other term is the 1 plus 1 over to the power of 1 plus 1 over 2k. And our method is advantage when L is at this little o complexity. So then, okay. So then we move on to introduce you the product formula. Actually, you can regard it as like I just mentioned before in the previous slide. Our goal is to want to construct operator U to approximate the evolution operator V, exponential minus IHT over R. Here we split the whole process into R step, and the distance between V and U is lesser than epsilon. So for the product formula, it means that we kind of use the product to approximate the evolution operator. So here, as an example, we can the first order product formula is it is shown in this way. So if the Hamiltonian, there are 3 terms in the Hamiltonian, then we can repeatedly, continuously implement the unitary operator. Like the first term is the exponential minus IH1t over R. The second term is exponential minus IH2t over R. The third term is the exponential minus IT3t over R. Then we this is one step. Then if we want to continuously repeat this process R times, then we can obtain the first order product formula for this quantum simulation process. And its gate complexity is at the order of big O t squared L cubed over epsilon. So actually, product formula is the way that we continuously implement the unitary operator so that we can, if the repeat the steps, if we increase the R, then the accuracy will be higher. So actually, we can extend it into the higher order product formula. Then it will be in this form. Then actually, we can iteratively construct the higher order product formula. Like for example, this single term is the first order product formula, and we reversely combine them together. Then we can obtain the second order product formula. Then we can concatenatively combine the second order product formula to construct the 2-case order Chorley-Suzuki formula. Then we can improve the accuracy of this product formula algorithm. So then its gate complexity is in this is the big O of the T over to the power of 1 plus 1 over 2k and L to the power of 2 plus 1 over 2k over T epsilon 1 over 2k. So then someone in the recent years, someone come up with an idea that because the quantum circuit that we implement in the previous, as shown in the previous slide, is deterministic. So someone come up with the idea that we can introduce some randomness into product formula. Instead of the fixed Schroeder operator, we can sample unitary for a given set U according to the probability. And then at this point, what we need to do is to try to minimize the distance between epsilon and V. Is lesser than big epsilon and V is less than epsilon. Epsilon is the quantum channel constructed by the artificially constructed by the randomness product formula, and V is the quantum channel constructed by the evolution operator. So which means that they need to design the corresponding probability and unitary such that the distance between these two quantum channels is close enough. So then in 2017, there's a mixing landmark, and which is from Earl Campbell. He said that how can we estimate the distance between the quantum channel big epsilon and V? And as it turned out that the error between these two quantum channels can be evaluated by the distance between evolution operator and each sample unitary, and also the evolution operator and the average of the sample unitary. And if we can find the bound respected these two factors, then we can bound the distance between these two quantum channels here. So actually, my work is based on this mixing lemma and trying to find better or trying to find a good probability and use such that evolution operator and the average of the sample unitary is closer enough so that we can improve the accuracy of the product formula. So here I gave you an example that the randomized formula proposed by Charles in 2019. It's quite simple. That here I give you an example. Like if we consider Hamiltonian is a H1 plus H2, and if we consider two kind of first order approximation, one is we put H1 before and the next is H2, and the other one is H2 is in front of H1. Then we can find that when we consider the second order here, there is some difference. One is 2 H1 H2, and the other one is 2 H2 H1. So here comes the error. Then Andrew Trust, they come up with a clever idea that why not we just mixing these two unitary such that this term will combine together so that we can improve the accuracy of the product formula. Then we can have the more accurate product formula algorithm. So then at this point, the distance between the evolution operator, the corner channel constructed by evolution operator and the corner channel constructed by randomized product formula is lesser than big O of T over R squared. So then they can repeat the same trick to the higher order Taylor formula. Then they gave this bound. So I try to simplify the formula and try to give you the concrete idea here. So as we mentioned before, we can use mixing lemma to bound the distance between on the channel. Then according to the randomized scheme proposed by Andrew Trust, we can have bound the distance in this sense. So at that moment when I read this paper, I asked myself that because this term is come from the distance between evolution operator and the sample unitary, and the second term is come from the distance between evolution operator and the average of the sample unitary. So I'm thinking that whether I can improve this term to make it also at the same order with the first term, so then I can improve the accuracy of the product formula. So then my motivation of my work is that can we design better a set of unitary and the corresponding probability such that the average of the unitary, the distance between average of the unitary and the evolution operator is at the order of 4k plus 2. So is there any question? So far, so good.
Yes, I'd like to ask for the example, we have the Hamiltonian equal to H1 plus H2.
Yeah, this term.
How you decide the density matrix rho? Is it you have to input some mixture state in here?
Actually, the density rho is like it's just the initial state of the quantum system. It could be the pure state or it could be the mixed state. So I just try to express it in general. This rho could be the pure state, but because here we want to use the randomized scheme, which means that when we implement the quantum circuit, we can pick this kind of operator with the probability 1/2. And when we repeat the quantum circuit next time, then we can repeat the same procedure and pick which unitary operator we want to implement. So in this case, there are two sample unitary. One is S1 and one is S1 prime. And we can pick both unitary with the probability 1/2. So actually, we need to repeat the corner circuit many times, and the effectively density operator, the distance between the effective density operator and the original state after the evolution operator would be is lesser than the T over R cube. So actually here, we're trying to introduce some randomized scheme to approximate the original evolution process. But here, rho could be pure state or it could be mixed state.
Okay, maybe I ask the question like this. You gave an example about the Born-Oppenheimer approximation.
Yeah.
Now, say for instance, if you consider the helium atoms.
Yeah.
With 2 neutron and 2 proton, right?
Yeah.
Yeah. So now in that case, is the Hamiltonian H1, H2 is something like the overlapping term, or I mean, if you want to apply this to the helium atom, then what will be H1 and H2 looks like? And in that case, yes, the rho is built up from the something like the hydrogen atom wave function. Can you give a more concrete example?
So what you
If
ask
I'm
is that if we
helium
consider
atom,
helium atom, so what
yeah,
H1, H2 would
yeah, and then
look
how
like?
about the rho? Yes.
Actually, because there are many steps there, like then we need to go back to the previous slide. Like for example, like if we consider helium atom, then we need to first, if we want to use this approximation, then we to see whether the mass of the nuclear is larger than electron. If yes, then we can, because the original Hamiltonian contains the kinetic of electron and also the kinetic terms of nuclear, and also the interaction between electron and nuclear, interaction between electron, and also the interaction between nuclear. And if we use this approximation, then we can regard the motion of nuclear as a fixed point. So then we can have this more simplified form here. So it depends on if, like in the helium case, if the nuclear mass is larger, way larger than the electron, then we can reduce in this form. And then we can like, and we can choose the basis here. So the phi and phi p and phi q is a basis that could be the SDO or STO3G or something else basis that you want to choose. Then we can calculate the coefficient here, HPQ and PQRS. Then once we have this coefficient is a predetermined value. Then we can transform. The remaining thing is that we need to transform this raising and lowering operator by using this transformation. Then there's a standard recipe that we can follow to transform this raising and lowering operator. So then we can, because this Q is we can express it in Pauli operator form, and this Z is actually the Pauli Z operator. So in this sense, actually, if we follow this procedure, the effective Hamiltonian of the helium would be like a tensor product of several Pauli operator and plus some tensor product of Pauli operator, etc. So it's quite complicated. So it would be like in this form. So I'm not sure if I answer your question, or so like
Okay.
yeah. So if
what
we
about the
can
density matrix? Is it built from the STO 3G wave function or something like that for the rho?
no, the density matrix that I showed here is actually the state that you want to, is the input of the state that you want to study. So like, for example, if you want to study how the state will change when it starts from some point. For example, the rho could be the ground state of the certain system, and you want to see how it changed after this evolution process. So the rho could be the electron state in the lower energy state of the electron system. Then you input it into the corner circuit. Like, for example, you can use some corner circuit to place it to represent the those electrons are in the ground state of the electronic system. So yeah, I think I should use this slide to be that actually is the figure to illustrate how we actually do corner simulation process in product formula algorithm. So here first we need to prepare the initial state, that is state you want to input. Then once we implement this gate consecutively, then we can, after then the last we can get the state that we want to study here. So this is the initial state, and after the evolution process, then we can get the final state that we want to study. So here is the state we need to input. So this could also be the mixed state or something else.
Okay, so what you're saying is in case of the helium atom, so one can take the electron. Yeah, we have two electrons, right? So you can take the two electron wave function of the helium atom as the input state. And then form the matrix, form the density operator.
Yeah. But because density operator, like it could be the pure state, and
right.
Yeah, so then we can use that procedure to realize
and then see how the two electron wave function evolve with the H1 plus H2 terms.
Yeah. True.
Okay. Thank you. Got it.
So then, okay. So my problem at hand is that we want to increase the error order of this term such that it is at the order of 4k plus 2. And here's our theorem. Then actually we can find a recipe such that B is the term that we showed here. We can increase it up to 4k plus 2 order. And the original term is still 2k plus 1. But because in mixing lemma, there's an 8th grade here. So actually, when we square the terms, then actually this term will also be in 4k plus 2 error order. And then when we add this term, this also 4k plus 2, then the whole effect is that we can bound the distance between V and the big epsilon is lesser than the big O of the E over R to the power of 4k plus 2 error order here. So here we could state it more formally in this way, like V is our target unitary, and we could design a set of unitary operator and its corresponding probability such that the distance between that is at the order of 4k plus 2. So yeah, I know it's kind of complicated here, but I'll just state the whole recipe for constructing our randomized product formula, and I will not show the proof here. And if you are interested, you can check my article on arXiv. So like for any product formula S2K, then we can define the D. D is the term that the V minus S2K. So then our first step is we want to know the terms of V dagger D plus dV dagger up to 4K plus 1. And we show that actually gamma would be the set of odd number up to 4K plus 1. So means that 2K plus 1, 2K plus 3, 2K plus 5, to 4K plus 1. And the even order terms here will be canceled out. And also we can choose the terms in this odd order term to be an Hermitian term. In this sense, then we can use the corresponding unitary U and probability P such that it can satisfy this formula. Then we can implement the quantum channel, which is the we implement UHL with the corresponding probability PHL, and our sample unitary is like a central structure. You can see here the first term is the original two-case order Chorley-Suzuki formula, and the last term is also the two-case order Chorley-Suzuki formula, and we insert a unitary between them, and this unitary can correct the higher order error of this product formula, such that when we average them, the error between our and the quantum channel big epsilon and V is lesser than 4K plus 2 error order here. So here's a quick remarks here. Actually, our recipe is also hold when S2K is replaced with an different kind of 2K order symmetry product formula. And also, actually, if we consider different form of application, implementing general correction unitary may be difficult. But when we consider quantum chemistry cases, that will be easier because, like we discussed before, for n-cubic chemistry system, we can transform it into a summation of Pauli strings here. Then the product of the different Pauli string is still Pauli string. So it will be easier for quantum chemistry cases to implement, to use our randomized scheme here. So here I gave you a simple example, like how our randomized scheme apply to the Hamiltonian equals to H1 and H2. And we aim to construct our randomized product formula based on this second order Chorley-Suzuki formula. And according to our recipe, that we need to know the terms up to fifth order. Like the third term is in this form, and the fifth term is in this form. And like I just said before, we show that the fourth term is vanished because some symmetry and time reversibility structure, so that it's automatically cancel out. So we don't need to care those terms. So then we just want to collect the information of the odd order terms here, like third and fifth order. Then we can construct the sample unitary based on this expansion. So then in the third order, we have this H1, H2, H1 over 48. And then we can use the this kind of unitary to realize it. And also for the fifth order term, we can group this term together to make it as a Hermitian term. Because in unitary, you need to make sure that the operator in exponential term to be the Hermitian operator. And also because we are in third and fifth order term, there would be an imaginary number in alpha 03 and alpha 05. So then we can follow our recipe to construct the corresponding probability P and so that we can construct a set of unitary and probability to achieve the error order 4k plus 2. So then the whole process would be like if we want to approximate our ideal quantum channel, that is V is the evolution operator, then we could sample the unitary from this unitary. That like U03 is what we construct in the previous slide, and U05 is the unitary we construct in the previous slide, and we insert it in between two Schroeder formula, and we pick like in each step if we want to try to find which unitary that we want to implement, we pick them with the corresponding probability P03 and P05, etc. So then in average, the corresponding quantum channel can denoted as a big epsilon rho can approximate the ideal quantum channel up to fifth order in lambda. And it remains the sixth order error. So then it shows we could when we follow our recipe, we can double the error order from 3 to 6. And the last is that we also do some numerical analysis. We choose the unsigned Heisenberg model, and we consider two scenarios. The scenario one is we fix the evolution time t to be n. N is the size of the Heisenberg model, and we change from n equal to 10 to 100. The scenario 2 is that we fix the size n to be 10, and we change time t from 0.1 to 10 to the power of 6. Then we have this plot. Blue one is the deterministic Schroeder-Suzuki formula, and red one is the randomized formula proposed by Andrew Charles, and green one is our method. So as you can see here, when we increase the size from 10 to 100, the number of exponential terms in our scheme is always larger than the other two methods. And when we also when we fix the system size and increase the time from 0.1 to 10 to the power of 6, the number of exponential is also lesser than the other two methods. So which shows that our method can reduce a lot of quantum resources compared to other higher order product-based algorithm. So in this sense, this could help us to save a lot of quantum resources if we want to simulate the quantum system. So here's the summary and the outlook. First, we propose a new randomized scheme for any symmetric polar formula, and our scheme can double the error order of the formula. And the third one is that our formula can perform better than the existing higher order formula when L is at the order of theta or T over epsilon to the power of 1 plus 1 over 2k. And the third point is that we kind of can extend this randomized scheme to combine with other Hamiltonian simulation methods such as linear combination of unitary or other Hamiltonian simulation technique, and it would be our future work. So thanks for your attention. So are there any questions?
Okay, yes, thank you, Paul, for introducing the randomized truth formula for us.
Okay,
This is a effective approach for reducing the resources.
Okay.
Yes.
Okay. So is there?
Okay, so I think now is the Q&A section, and see if any questions from the audience.
Yeah, I know it's a little bit too complicated because it's a lot of mathematical details here, but I'm trying to make it simple. Quantum simulation is very important for quantum computer, and we need to find the efficient algorithm to achieve to approximate the operator. So that's our main goal here.
Yeah, okay. Could you repeat one more time how you select the unitary operator?
Oh, you mean in my okay,
Yeah,
I use this example like
the
in
sets
our
of unitary, yes.
yeah. So actually our unitary is in this standard-like form. We insert a unitary in between the Schroeder-Suzuki formula. And there's two things we need to check. Like first, this U should be unitary. And so we found that we can expand this term, like identity minus V dagger D minus dV dagger. And here V is the evolution operator, and D is the let's show here is the evolution operator minus S2K. S2K is the Schroeder-Suzuki formula. Then when we expand V dagger D plus dV dagger, then we found that actually the even order term is cancelled out automatically. So that it leaves the odd order term, 2k plus 1, 2k plus 3. And it gives us it's convenient that because it's even order term, so then there must be an imaginary term, imaginary number here. And what remains is that we need to group the operator term into Hermitian term. So then we can use the unitary to recover the term up to 4k plus 1 order here. Yeah, because we want to make sure its Hermitian is that the unitary that we insert should be also the Hermitian term here, and the alpha should be the imaginary number here. So then in this okay, so then in this sense we can guarantee that when we expand this unitary, it will be the identity plus alpha H plus the alpha square H2 H square. And zeroth order term and first order term will be the term that we can recover in V dagger Dn plus dV dagger.
Yeah, okay, I see. All right. Okay, it's almost 1 hour since we start. So I'd like to ask if any other question from the audience. Okay, if not, then once again, let me thank Paul for introducing the randomized toaster formula and teach us how to make use of this technique to achieve a better approximation for simulating the Hamiltonian.
Yeah, thank you.
Okay, all right. Thank you so much.
Then I stop sharing my screen.
Yeah.